Hi, today I'm going to start to talk about the equilibrium of the rigid body. Remember previously we talked about the equilibrium of a particle if all the forces applied on a single point, and we will look at that how that single point would be in equilibrium. This time we are looking at an object and see how, if we have the rigid body, how that rigid body would be in equilibrium. In general, we want an object to be in equilibrium. There are two equations that we need to satisfy. The first equation is that all the forces applied on that as a vector should be zero if we add all the force together, and also if we add all the moment together as a vector, they should be zero. So in general, these are the two equations we have to have. So the resultant force in a vector format should be zero. In other words, all the forces should cancel each other. And all the moment in the vector format, if we add it together, should be zero. Other for the resultant moment should be zero, or all the moment would be cancel each other. But when we will come to the 2D rigid body, we can write this equation instead of having it in the vector format. We are going to write them in a scalar format. So we can write them in general as three equations. And those three equations are sigma f x is 0, sigma f y is 0, and sigma m about point O is 0. So what it says that if we are in 2D, so we don't need to be worried about the vector format, we just look at the values of all forces and the moment. And we said that all the forces along x direction should cancel each other, so we know that our rigid body doesn't move in the x direction, or if the x is in the horizontal, it doesn't go left or right. All the forces in the y direction should be cancelled out and should be zero. So in other words, our object doesn't move up and down. And all the moment about any given point, so the point O can be any point, all the moment about any given point should be zero, so our object doesn't rotate. In other words, these three equations says that the object doesn't go left or right, doesn't go up or down, or doesn't rotate. One more to just remember that the point O that we are talking about, that the O can be any point. So this is probably the classical form of writing them, but we can write these three equations in different format. One other format is that instead of having two forces in the x and y direction and one moment, we are going to have one forces and two moments, and it's going to be looked at like that. So we are going to write it as sigma f x is 0, and then sigma m about point A is 0, and sigma m about point B is 0. And remember, the only point here is that the A, B should not be parallel with the y-axis. The only restriction we have here is that. So the AB should not be parallel with the y-axis. So in other cases that we will write that sigma of x is equal to 0, so we cancel out all the force in the x direction, and then 2 points, any 2 points. I will write the moment about point A and point B, any 2 points. As long as A and B are not parallel, AB, the line AB is not parallel to line in a y direction, we are good to go. Similarly, we can write the other sets of that. So we can go ahead and start and write, instead of that, we can write sigma if y is 0, sigma m about A is 0, and sigma m about B is 0. And again, as long as AB is not parallel to x, so we can write, we make sure that all the forces we have on the x direction, so if I draw the line here, so all the force in the y direction is 0, and again any 2 point A or B, any 2 given point A or B. So if we write the moment about them and these three equations, if we satisfy these three equations, then the object is in equilibrium. And also we can write it in another form to make sure the object is in equilibrium. This time we are going to write it as sigma m about A is 0, sigma m about b is 0 and sigma m about c is 0, and the only thing is that a, b, and c can be any 3 points, The only restriction is that there should not be on the same line. So as long as A, B, and C are not on the same line, we can write the 3 moment to make sure that the object is equilibrium. In other words, as long as the ABC form a triangle, so we can write also this equation. So if you look at here, we pretty sure can write it in 4 formats. So it can have sigma fx, sigma fy, and moment about any given point, or sigma fx and 2 moments about 2 points, sigma fy or 2 moments about 2 other points, or 3 moments or 3 points about 3 points. We can use any of these formats to make sure that the object is in equilibrium. And also one word says, so you can mix and match it. They don't need to be exactly in the same order. So for example, here we may start with the fy and then we do the moment and then do the fx, or here we may start with the m over a, then do the sigma f and then go to the m over b, or here start from c, then b, then so we can go it any order. So basically these 4 format that I write it, we can mix and match it in any way we want it. We can use it in any format, in any order, to solve the problem. The only thing is that we have to look at the problem and see which of these equations is going to give us the easiest way to solve that problem. And most of the problem is like that. So you are given an object and there are some external forces on object, and you are asked to find the reaction of the support so that object be in equilibrium, so that object stay in its place. So you have external forces, you use any of these sets of equation to find the reaction of the support that hold that object in its place. One thing about when we are choosing about f in x and y direction, there are not much, so you just write and cancel out the 4. But about the moment, sometimes we can choose which point we write the moment to make it easier to solve the problem. So assume that, for example, I have an object here and I have 2 points, A and B, and I have 3 points going to A, and I have, for example, 1 force going to, so it's the F1, and F2, F3, and F4. So if I want to find the F1, if I write the sigma fx and sigma fy, so I'm gonna have component of all 4 forces. But look at here, if I write a moment about point A, if I write this equation, sigma, if I write sigma m about A is 0, if I write sigma m about A is 0, then what I have, all F2, F3, and F4 pass through point 8. Because they all pass through point 8, so their moment is going to be 0. The only force has the moment about point A is F1. So if I write the sigma m about point A, all F2, F3, and F4 would be eliminated from my equation because they all pass through that point, and the only point that would be left is point B. So I can would most likely come up with a simpler equation. So when we want to choose the point that we write the moment, for example here or here, if I have the fx, fy, the point O that I want, most of the time choose the point O to eliminate most of the unknown or most of the forces. So you are gonna have a simplified equation to solve. If you choose it very wisely, in most cases you can eliminate all the unknown except one, and so you are going to end up having one equation, one unknown in that equation, so you can get that unknown very easily. So that's very, when you have a problem, spend a little bit time and look at which point would be the best to take to calculate the moment about that point. One other point I want to make is that when we are dealing with 2D problems, in most cases, I don't want to say in all cases, but in almost most cases, the easiest way to solve that is that before doing any calculation, before using any of these equations, find all the forces component along x and y axis. So in other words, if you have forces or reactions, the support reaction that they are not in the x or y direction, find them first, find their component in the x and y direction, then start to do any calculation you want to do. And I'll just give you a simple example how to do that. So most of the time you know how to do that from your trigonometry course, but here I'll just show you a simple trick in case that you forget that. So assume if this is a x and this is a y, and I have an angle, I have a force F with angle theta. So always remember the component that is next to the angle, or the component touches the angle, which is going to be here. So that component which is touching the angle, here is going to be fx, is f cosine theta. So the one is next to the angle or touching the angle is cosine. The one is away from the angle or does not touch the angle, for example here, a bit red. So the one that does not touch the angle here, so this one does not touch the angle, is away from the angle, is going to be sine theta. So it's easy trick to remember, that component that is next to the angle or touch the angle is cosine. That component that is away from the angle has the sine in that. Similarly, if I'm going to draw another example and assume it's flip. So again, if I have a x and y, and I have the force here, that's the F, and this time assume this is the theta. This time again is going to be the same thing. The one that is touching the angle, the one that is next to the angle, which is going to be, this time is going to be here. This is F cosine theta, which is going to be Fy here. So the one that touched the angle is cosine, and the one that is away from the angle, does not touch the angle, which is going to be this. So this one is going to be Fx this time, so it's going to be F sine theta. So always remember, if you have the component that touch the angle, you use the cosine to find that component. If you have the component that does not touch the angle, is away from the angle, is going to be sine. The same here, the same here. So we can draw the line here, so these two are separate. So these two are that you can consider. Here again, this one touch the angle is cosine, this one does not touch the angle, so it's going to be sine. Here the vertical one touch the angle, so it's going to be cosine. The horizontal one doesn't touch the angle, so it's going to be sine. If you have any other orientation, always remember that the component that touch the angle is right sitting next to the angle. Use the cosine theta to find it, and the component that is away from the angle, we will use the sine. We will use the sine to find that component. Okay, let's look at an example, see how we can find, how we can use the equilibrium of rigid body in our problem. So assume here we have a beam that are supported with two supports at point A and point B, and there are three forces applying on that. And we want to find the reaction of support at point A and point B if this beam is going to be in the rigid condition, in the equilibrium condition. So the first thing when we want to solve this problem we need to do is to draw the free body diagram. And remember, when we want to draw the free body diagram, we just need to first of all disconnect the body from any object and draw the object, which is going to be here a beam itself. So I'm going to draw the object, so the beam. So that's my object, and that is a beam that I have. And then we're going to start to adding external forces that wants to move that object. The external forces that want to move that object is, one of them is this 200 Newton, one of them is that 50 Newton, and the other one is that 100 Newton at the end. So these are the three, and this is going to be 30 degrees. So these are the three forces that wants to move the object. After I put all the external forces that want to move the object, I have to add the reaction from the support that wants to hold the object in place. So let's look at the point A. The point A is a pin, and you remember when we were talking about the pin was like that. If you consider this marker, so the pin doesn't let the marker move left or right. It doesn't let it to go up or down, but it lets it to rotate. It doesn't restrict it in rotation. So to make sure that point A doesn't go up and down, I'm going to add a reaction AY to make sure that it holds it in a y that doesn't let it go up down. The direction I chose for AY, I just assume it. It might comes up negatives in calculations, so we know that what we chose here is wrong and it's going to be opposite. The same here, the pin doesn't let the beam moves in the y or in the x direction, doesn't let it go left or right. So I'm going to add another forces here, another reaction here in the x direction to make sure that beam doesn't move in the left or right direction. Again, the direction I just assume. For the point P is the roller. The roller, the only direction the roller restricts is normal to its direction. So if the roller, the normal direction to that door is up and down, so it just restrict that beam moving up and down. It doesn't restrict that beam to moving from left or right. So the only force I need to have here to make sure it's not going up and down, I add one force By here to make sure that at the point B, my beam is not going up and down. At point B, it can go left or right, so I'm not going to restrict it. In that way, also point A and point B doesn't restrict the rotation of that beam, so I'm not going to also restrict the rotation of beam. So these are my reactions. So the external forces and reaction. And now I want to find the reaction. Even before I start to anything to do, as I said, probably the best thing we need to do in 2D is to find the x and y component of all forces. So we have all the reaction are in the x and y direction, and we have these two also are in the y direction. So the only one is not is this 101. So we are going to find the component of that, which this one is touching the angle 30, so it's going to be cosine 30, and this one, which is away, this component which is away from the angle, is going to be 100 sine 30. So these are our two components. Now that we have all the forces in x and y direction, the next thing we need to do is that we need to go ahead and see which of the equilibrium equation we need to use to find ax, ay, and by. If I look at first, I have to see if I write that sigma fx is 0 is the best choice for the first equation, sigma my is the best choice, or sigma moment about any point would be the first choice. So if I look at that here, I will see that the only force I have in the x direction is this component and this component, these two. So probably writing the sigma fx is really good point to start, because there's only one force and one unknown, and it's going to be very easy to solve it. So if I go ahead and write the sigma fx is 0, then all I have is ax, which is in the positive direction of x, and then the 100 cosine, which is in the negative direction, minus 100 cosine 30, and remember this theta is 30, this theta is 30 is 0. So AX is 100 cosine 30, and there is going to be 86.6. 100 cosine 30 is going to be 86.6 Newton. So that's one unknown. So the AX, we know the AX, and we find the AX. Now we need to find the AY and BY, and we'll see which equation we can use is gonna be the best. If I write the sigma Fy is 0, then I am gonna have, because AY and BY they have two unknown, then I have end up with two unknown in my equation, because AY and BY both of them are unknown. So instead of writing the AY, the F in the Y direction, sigma Fy is 0, I probably better to use a moment equation first. If I look at here, which point would we eliminate the unknown? If I write the M about point A, AX and AY would be eliminated because both of them pass through point A. And if I write a moment about point A, the moment of AX and AY would be 0 because both of them pass through point A. If I write a moment about point B, then the moment of BY is 0. Also, the moment of AX is 0 because the AX also passed through point B. So the moment of BY and AX both is 0. So I can write either of them, and if I write for about point A, I can find the BY. It's going to be only unknown. If I write the moment about point B, the only unknown is going to be AY I can find. So I'm going to write sigma M about point A. So if I write the sigma M about point A is 0, and assuming the counterclockwise is positive, then I start to write it from here. So about point A, so what I have is a 200 Newton, and about point 8, this 200 Newton rotates the beam about point 8 in a clockwise format, so it's going to be negative. And the distance, the normal distance between point 200 and A is just 1 meter, so it's going to be 1. Then I move to 50, so then 50 Newton. The distance, the normal distance between 50 and point A is just this 2, so the distance is 2. And this one also about point A, assuming about point 8 is going to rotate it clockwise, so it's also going to be negative because we assume counterclockwise positive. And then I write this one 100 sine 30, 100 sine 30, and the normal distance is, if you look at it, is 4. This is the normal distance from here to here. So the normal distance is 4, and again it rotated clockwise, so it's going to be negative. And then the 100 cosine theta is going to be 0 because it passed through the point A. So I have 100 plus 100 cosine 30 times 0, because it passed through point A, so its moment is going to be 0. It doesn't have any moment. The AX and AY also doesn't have any moment because they pass through point A. The only force left is BY. So I'm going to write BY. And the normal distance from BY to point A is 3 times 3. And it rotates the beam respect to point A, about point A, in a counterclockwise. So it's going to be positive. So if you look at this equation, the only unknown is BY. So everything else is known. So if I solve that equation for BY, the value I'm going to get is 166.67 Newton. Now that I have BY and AX, the only unknown left is AY. And again, I have to go and see. Okay, I already use FX. I already use one moment. Now I can, for the third equation, either I can use Fy is 0, or I can use another moment equation, one of these two, to get all three equations. So if you look at here, probably the easiest one is to write the sigma Fy is 0, because we have everything else is known except for Ay. So if I write that sigma Fy is 0, so I start from that end, so it's going to be Ay. So first I add all the external forces. So it's going to be negative 200 because it's moving, pushing it down. Negative 50, also pushing it down. Negative 100 sine 30, which is also pushing it down. Plus Ay plus By, 0. And we don't have any other forces. And here we already know the value of By. The By, we know it from up there. So we know that By is 166.67. The only unknown is Ay, and so we can find the Ay is equal to 133.33 Newton. So we can find the Ay in this equation. Again, remember, this is I use the Fx, sigma m, and sigma Fy. So I think this is probably the easiest order you can use, but you can use any other combination or order that you want. For example, we can use two moments, one moment about point A, one moment about point B, and for example sigma Fx, or any other combination of the those sigma Fx, sigma Fy, and sigma m. Any combination of these three that gives us the solution, we can use it to find the reaction. So one more time, very quick through what happened here. So we draw the free body diagram first. So in free body diagram, we draw the object, we remove every connection, any forces. Then we add external forces on that object. Then we add all the reaction from support that wants to hold the object in the place. So the external forces that want to move it, the reaction object that wants to, the reaction from the support that wants to hold it in the place. So we have the object and all the external forces and reaction. And after that, before we start doing anything, we find all the forces in the x and y direction. And then we will look at each of the equations, see which equation will serve us best. So we write first the sigma Fx is 0, then we write the sigma m about the point A is 0, and then we find sigma Fy is 0, and we find all Ax, Ay, and By values, which will represent the values in the support A, support the reaction of the support A and the reaction of the support B. Now let's look at another example. So we have a beam again here supported by reaction, supported with point A and B. So at point A and B is supported, and it has 100 Newton single force applied here, and the triangle distributed load with 50 Newton per meter also applied here, and I have a single moment applied on that one, the 150 Newton meter at that end. Now we want to find out if we have these two forces and the external moment, how much is going to be the reaction of those support at point A and point B. So the very first step, again, draw the free body diagram. To draw the free body diagram, remove everything, disconnect it from anything, and draw the object, which is going to beam here. So I'm going to just draw that beam. So that's my beam. Next, I will put all the external forces on that. The external forces I have is 100 Newton here, apply here. This is the 100 Newton. Then I have the external rectangle forces here. It's going to be 50 Newton per meter. And then I have this external moment here, which is going to be 150 50 Newton meter. So these are the external forces and external moment I have. Now I have to add the support from the reaction from the support. So it said these are the external forces and moment that actually wants to move or rotate the object. Now I have to add a support, the reaction from support that actually want to hold the object in place. So if you look at at point A, it's a roller, and when it's the roller, the roller is on keep the object from moving up and down. It doesn't restrict it in the left or right direction. It doesn't restrict it from the rotation. So the only support I need here, the only reaction I need to add here is AY to make sure that point A is not going up and down and holding it place. So I don't restrict it to go left or right. I don't restrict it from rotation. The point B is the pin. The pin restricts the object from going left or right or up and down. So it doesn't let it go left or right, it doesn't let it go up and down. So I have to add one reaction to make sure it's not going up and down. So BY, and I have to add, so BY, and I have to add another one, BX, to make sure that's not going left or right, so to hold it in place. So these are all the forces these are all the external force and moment. These are all the reaction I have. Before I start to do anything, again, here, everything is in the X and Y direction, so I don't need to find the components, but I have a distributed load here. So before I start to do that, let's convert that distributed load, find the equivalent single load for that distributed load before I start to work on that. If you remember, when we were talking about the distributed load, the magnitude of the distributed load is the area under the load. So the area of under that load is the area of this triangle. And for the triangle, what I have here, so I have a triangle like this, that its length here is 1.5, and this height here is 50. So the area underneath of that is half of, so the force, the equivalent force here is equal to area is half of 1.5 times 50. Times 50, which is going to be, the magnitude of that is going to be 37.5. So it's going to be 37. So that's the magnitude of that force. Where it's going to be applied, remember I said when we have the triangle, therefore if we have a triangle, the distance is always is 1/3 from the base. So it's going to be 1/3 from the base. So in other words, let's draw another triangle so it's easier to. So if I have a triangle here, and this is the L, the centroid is at L/3 respect to that edge. So this is the centroid, and we know that FR is always applied at at the centroid. The distance of centroid is L/3, so we know that distance is third of that L, so this distance is L/3. So that's where that force is applied. So the magnitude is the area underneath of the distributed load, and the location that force is going to be applied is going to be right at the centroid. So I'm going to replace this distributed load with a single load, and that single load is going to be so I'm going to just remove that one and replace it with a single load. So I keep it in place, the outline, so I have a distributed load here, and it's not right. So I have a distributed load here, and I replace that distributed load with a single load, which is magnitude is going to be 37.5, and the location is going to be applied. So if you look at here, it's 1/3 from this end, and it's going to be 2/3, so it's going to be 2/3 from the other end. So if this is the L, this is 1/3, and this is going to be 2/3 of L. So the distance what I have here from the point B, this distance here from point B is 2/3 of 1.5. So it's going to 2/3 of 1.5, which is going to be just 1. And so this is 1, or the other part is going to be only half. So this is where it's going to be located. So this one is 1, and this part, the other part here, is 1/3 of 1.5, which is going to be 0.5. So this is this one. So that's the location that force applies. So it's the 1/3 from the base and 2/3 from this point. So it's going to be 1 from here and 0.5 from here. So it's the location of that single force. Now that I have all the external forces and all the external support reaction all in the x and y direction, I can start to solve the problem. Now when I want to solve the problem again, I have to look at which equation serve me better. If I come here and look at the sigma fx, the only force I have in the x direction is bx. There's no other force that I have. So probably it's the best to start with sigma fx. So if I write the sigma fx is 0, what I'm going to get is that the only force I have is just bx is 0. And that's it. So I already found one of my forces. Bx is 0. Now I have to find ay and by, and if I write the sigma fy is 0, the problem is that I'm going to have ay and by both unknown. So I have one equation, two unknown. So it's better to go ahead and find and use the moment instead of using the fy. So the moment, again, I can use the moment about point A or can use it about point B. Either of them works. So if I write it from about point A, the moment of ay about point A would be 0. So ay would be eliminated from my equation. And the bx is also 0. Also it passed through point A. So the moment of bx is also 0. So the only one has the moment about point A is going to be by. So I'm going to write the moment about point A is 0. And I write everything counterclockwise is positive. So if I start from here, I have 100. So I have a 100 Newton. And the distance with A is 1.5. The normal distance is 1.5. 1.5. And it's rotating it respect to point A, it's rotating it clockwise. So it's going to be negative. Then I have 37.5. And the distance to point A, I have 1.5 here, 1.5 here, and also I have 1 here. So it's going to be 3 up to here and 1 here. So it's going to be the total distance from here to here is going to be 4. 1.5, 1.5 plus 1. So it's going to be 4. Also, this one rotated clockwise. So it's going to be negative with respect to point O. Then I have this 150. And that's just moment itself. So I don't need to do anything. I just need to add it or subtract it. So I had 150. And this 150 rotate clockwise. So again, it's going to be negative. So it's going to be 150. I add it, just simply add it. No need to make any other change. And then I will come here, and the only one is left is the by. So I wrote the by. And the distance from by to point A is 3. The normal distance is 3. So times 3. And if you look at it, respect to point A, is going to rotate it counterclockwise. So it's going to be positive. The bx0 also, it goes through point A, it doesn't have a moment. The ay goes through point A, it doesn't have any moment. So it's going to be 0. And if I solve that, then I will get the ay is equal to um, sorry, I will get the By equal to 150 Newton. So the By is going to be 150 Newton. Now I have By and Bx, the only one left is the Ay. So the easiest one equation to find that, remember I already used the Fx, I already used one of my moment equations. So the only one left for me, either one more moment equation or Fy. Probably it's easier to use the Fy, so I'm going to write the sigma Fy is 0. We can write the sigma m about point B0 as well to find the Ay. So either of them is okay, but sigma Fy probably is easier because everything is going to be just add and subtract. Don't need to calculate any moment. So if I write the Fy is 0, first I write the external forces I have is the negative 100 here, and then negative 37.5 here. And remember, the moment is not going to show. The moment always shows in the moment equation, so we don't care about that. And then we have negative Ay because it's going upward, and then negative By, and it's going to be 0. And we know the By is 150 Newton. So if we solve it, then the Ay would be comes out and negative 12.5 Newton. And the reason is that it comes negative is that because we assume the Ay is going upward. But if you look at this force wants to rotate the object about point B. So it wants to rotate the beam about point B, and that end wants to move up. So actually the support point H should to pulling it down. So the direction of the A actually should be downward because this force wants to make it rotate about point A up, and the B wants to bring it back, hold it in the place. The A wants to bring it back, hold it in place. So the A should be downward to cancel the effect of this 50 Newton about point B. So, and that's why it comes out negative here, that we will see the negative sign here for this problem. Let's look at another example. Here I have a beam that goes from point A all the way here and then bended down, and it's fixed at point A, so it's the support at point A is fixed. The external forces, I have the distributed loaded on the horizontal part of the beam, and then I have these forces applied to the right at the very end of the beam, 200 Newton here. So there's the 200 Newton. The total length is 3 meters, and that slanted part is 1 meter. So I want to find the reaction, all the reaction at point A. Again, the first thing we are going to do, draw the free body diagram, and draw the free body diagram is just remove everything and just draw the object itself, so which is going to be. So that's the object. So to remove everything, the only thing I'm going to draw is the object. Then I'm going to add all the external forces applied on that. For the external forces, one of them I have is these 200 Newton here. And then I'm just first going to draw the outline. Then I have this external 100 Newton per meter distributed load, and for that 100 Newton distributed load, it would be applied here. As I said, it's much easier when you are dealing with distributed load. It's always easier to replace it with a single load rather than having as a distributed load. So when I want to put the external forces, I'm going to replace this distributed force with a single distributed load with a single force. At that single force, remember, if I call it the Fr, the magnitude of that force is going to be the area underneath of this rectangle. This rectangle has a length of 3 and the height of 100. So the length of 3, height of 100. So the force is going to be the area of it's going to be so the force, the resultant force from the distributed load is the area, and it's going to be 3 times 100, so it's going to be 300 Newton. So this is the length of the triangle, and 100 is the height of the triangle. So the total load is going to be 300 Newton. And where it's going to be acted, that force, the resultant force, is always acted at the centroid of the distributed load. The center of the the center of the triangle is right at the center of the triangle. So it's going to be right at the center here, which is going to have the distance of, so if the total is 3, it's going to be 1.5, and it's going to be 1.5. So that point is right in the center of that triangle, and the magnitude is the area underneath of that. So that's the force I'm going to have. So I replace that distributed load with a single load equal to 300 Newton. So it's a 300 Newton and applied on the centroid. One more time. So the magnitude of the distributed load is just the area underneath of that load. The area underneath of this load is the length times, because the rectangle, so it's the length times the height. Length is 3, height is 100, so 3 times 100 is 300 Newton. Where it's going to be applied? On the centroid of that distributed load. The distributed load is the rectangle. So the centroid of that rectangle is right at the center. So it's going to be applied at that center. So it's going to 1.5, 1.5. So these are our external forces. Now we need to replace the reaction of the support. So make sure that the object stays in place. So remember, in the free body diagram, when we draw the free body diagram, just draw the object, then put all the external forces that wants to move the object, then add all the reaction from support that wants to hold it in place. In the fixed, when we have the fixed support, we know that the fixed support is always like that. It's like I hold that marker like that. It doesn't let it go left or right. It doesn't let it go up and down. Also, it doesn't let it rotate. So I have to add one force, because it doesn't let it go up and down. So I have to add one reaction in the y direction. And as I say, I just assume the direction. We do the calculation. If it comes negative, it means the direction I assumed was not correct, and it's actually opposite. Then it also doesn't let it to move in the x and y direction, so I have to add one to make sure it's not moving in the x and y direction. It doesn't go left or right. Also, it doesn't let it rotate, so I have to also add the moment to make sure it's hold it there and doesn't let it rotate. So I have to add also m at point m here, so to make sure that it does not rotate at that point. So I have all my external forces, and I have all the support that want to hold it in place. So the AY doesn't let it go up and down, the AX doesn't let it go left or right, and the M doesn't let it to rotate. Now I'm going to start to solve this problem. Again, I have to look at, if I want to find AY, AX, and M, I have to look at which equation is going to serve me better. So I can write Fx is sigma Fx is 0, sigma Fy is 0, or sigma M about any point is 0. If I look at here, one more thing before I start. Again, here we have the force that is not in the x and y direction, so I have to write it in the x and y direction. So I'm going to find x and y component of that force. So if I look at here, if I draw the line here, so that's going to be 30 degree here. That's the 30 degree, so that's going to be 30 degree. Now, the side that is actually, this side that is actually touch the angle, so it's going to be cosine. So this one is touching the angle, so it's going to be cosine. So it's going to be 200 cosine 30. And the other side, which does not touch the angle, is going to be sine. So this component is going to be 30. This part, which does not touch the angle, is away. So it's going to be 200 sine 30. And also, I probably later on need the dimension of this part. So again, if I look at this part and I want to find the direction of this part, if this is a 30 degree, if this is a 30 degree here, also this is going to be 30. This is going to be 30. So, and this one comes all the way up to here. Now I need these lengths and that length. To find these two lengths is again, this component is touching this component touching the angle, so it's going to be, and this length is 1, so it's going to be 1 cosine 30. So this length, and this length is away. It does not touch the angle, so it's away. It's actually here, so it doesn't touch the angle. It's here, so it's going to be 1 sine 30. So these are also these two distances that I probably needed later. Now the question in this problem is that to find the support at point A. Again, I have to go and look at, after I have my free body diagram, I have to look at which equation, if I use the first, is the best one. Sigma f x is 0, sigma f y is 0, or sigma m is 0. Which of these is the best to use? If I look at here, if I look at the x direction, the only unknown I have in the x direction is ax. So I can start with sigma f x 0 because I only have one unknown, so it's easy. So I have ax, which is in the positive direction, minus the only active forces I have here in the x direction. The other forces is negative 200 cosine 30 is 0. So therefore the ax is 200 cosine 30, which is going to be 173.2 Newton. So that is the fx. Now I have to go and see, I want to find the ay and m, and which equation is going to be easier to do that. Again, if I look at there, probably the easiest one is just to write the sigma fy, because the only unknown I have in the y direction is ay. So if I write the sigma fy is 0, all the forces I have in the one, so I have this 200 Newton, which is going downwards, so negative 200 Newton. And then I have this 200 sine 30, which is going upward, so it's positive, so it's plus 200 Newton sine 30. And then I have the ay, which is going upward, is also plus. Ay is 0. And if I solve that equation, then the ay, because the only unknown is ay, if I solve that, it's going to give me is equal to 200 Newton. So I already find ax and ay, so I need to find the moment. And to find the moment, probably the best point that I can calculate the moment is point A, because if I calculate the moment about point A, ax and ay would be cancelled out, and I can write everything else. So you can write the moment about any other point as well. Here I start to write it from point A. So sigma point A is 0. Again, I assume counterclockwise is positive. So about point A, I have these two, I start from this one. So I have 300 Newton, and it is respect to point A, the distance that has the normal distance is 1.5, and it rotated it clockwise respect to point A. About point A, it's going to rotate clockwise, so it's going to be negative. Then the next force I have is this 200 cosine 30, and I want to find the distance of the normal distance. Again, when you want to find the normal distance of force and you cannot find it, just directly extend the line of action. So extend the line of action to point A, and this is going to be the normal distance. So this is the normal distance for that. So this normal distance is 1 sine 30, as we have it here. So it's a 1 sine 30. Extend the line of action to point, and then there are the normal line from the point to line of action. So it's going to be 1 sine 30, that distance. So the distance here, we have it is 1 sine 30. And which direction is rotated? Again, if I look at respect to point O, this force is going to rotate it clockwise, so it's going to be also negative. Then I have these 200 sine 30, and want to see, so 200 sine 30, what's the distance from here to point A? So again, if I can't find it, extend the line of action. So I'm going to extend the line of action for this force, and then find the normal distance from the point A to there. So that's the normal distance from point A to that line of action, and it's going to be 1.5 plus 1.5 plus 1 cosine 30. So it's going to be so if I want to write it, it's going to be times 1.5 plus 1.5 plus 1 cosine 30. So that's the total distance from here to here that we have. So I write for this force, I write for this force, I write this for this force. AX and AY pass through the point, so they don't have any moment, and the only one left is the M. And the M I consider here, I draw it clockwise, so it's going to be negative M, because it's a clockwise, and it's going to be 0. And if I solve all the solve these problems, this equation is going to give me minus 150 Newton meter. So I get minus 150 Newton meter for M. And probably we could see it should comes out negative, because these forces and these forces want mostly rotate the object clockwise, so that M should be counterclockwise to hold it in place and prevent it from moving clockwise. So the M should be counterclockwise to cancel the clockwise rotation from these two forces. So that's why we assume it clockwise, it comes out negative, it means that it should be counterclockwise. So that's how we, so in this case, we draw the free body diagram, put all the external forces, but put all the reaction from the support that wants to hold it in a place, and then find all the forces in the X and Y direction. And then we write sigma of X, sigma of Y, and sigma M to find the reaction unknown. Again, we can mix and match these, we can play with these three equations and see, sometimes we may find it easier way to find that equation. So in this problem, I could write fx, fy, and m about point N to find the unknown reaction at point A.